So in the last class we talked about ergodicity and we gave an interpretation in terms of decomposing the space into ergodic components. If something is ergodic if it cannot be decomposable anymore. In this class we're going to talk about ergodicity uh, in a different perspective, and the perspective that ergodicity is one extreme, is giving some idea that things are mixing, that things are somehow close to independent. So we'll draw a line by the end of this lecture where things here could be completely dependent, but then they can be ergodic, then they can be mixing, then they can be quantitatively mixing, and then they can be IID. So this is one way to see ergodicity as one step uh, towards independence. But this, of course, is very informal. It doesn't make much sense. But we're going to make some statements that are rigorous and give this feeling. But before, we have to define what mixing is. And we're going to do this in the context of uh, environments that are defined on Z. So not starting from 0, but going from minus infinity to plus infinity. And one way to see this is to see this array omega as a function from Z to your space. So having this, we can define already two important things. So we say that omega, or P, which is the law of omega, is strongly mixing with respect to the shift. By the way, P, as I said, is a probability on S to the Z. If the following happens, you take any event A that is measurable with respect to the canonical projections from minus infinity all the way to t. Okay, so if you think of z as a line, t is some value here, A can read everything to the left of t. And B is another event that's going to be measurable with respect to everything after t plus s. So here this distance is s, here lies t plus s, and B can read everything from here on. So we have these two events that are somehow far apart. They have distance s between them. And what we want is that these two events are kind of independent. So we want the probability of the intersection, A intersected with B, to be close to the product of these probabilities. Probability of A times probability of B. So if this was 0, there would be independent events, but we don't expect this to be exactly true. We just expect that for any t in Z, the supremum of this quantity should go to 0 as s goes to infinity. So again, we are dealing with something that's uniform over t, uniform over all events A and B that rely on the projections further than S from each other. So A depends on this, S and B depends on this, and there is a distance S between them. And this is going to be roughly independent as S goes to infinity. So this is the notion of strong mixing. And we now go to the definition of mixing, which is slightly more complicated, but not much, because there will be another parameter here. So again, we take this, we're going to take P on S to the Z. It's said to be mixing. Of course, again, with respect to the shift. If again, there is a supremum, but now the supremum, okay, of the same quantity, P of A inter B minus P of A, P of B. This doesn't change. But now we're going to have events A and B that are slightly different. So A can depend on anything from T minus K to T. So it's not depending on infinitely many projections anymore, just finitely many of them, and within a distance of K. And B is also from, X, T plus S until T plus S plus K. And since the supremum depends on K, because it doesn't depend on T because T is inside, so this supremum is some function of both K and S. Okay? And what we expect is that B K of S goes to 0 with S for every K. So now the picture is something like this. We have an event A that depends on everything here that has length K. Then we have a gap of S until we start to look at B. And B can also look into K variables. And we are letting S go into infinity with K fixed, and we want this to be roughly independent. And this should hold for every K. So this is not exactly the same definition as above. We can find examples where these two are not the same, but they're quite similar, especially from the perspective of strong mixing that we're gonna mention now. But first, let's look at some examples of mixing. So the first example would be to pick reversible. So of course the first example should be example 0, something is IID. Then all of these are actually independent. There's nothing to prove. But for a more interesting example, suppose that we have a reversible Markov chain on a finite state space. And since it's reversible with respect to a certain measure, right? So let's call it mu reversible. We can define the doubly infinite process that goes all from minus infinity to plus infinity and is stationary. How do you do this? You just pick x0 according to mu, and you let the process evolve to the right and to the left independently, and this is going to be a Markov chain on Z on doubly infinite trajectories, and this will be stationary with respect to the shifts. And not only that, if you pick, since our state space is finite, if the chain is a periodic and irreducible, it's gonna be mixing, strongly mixing actually. So the fact that it's Markovian makes the notion of mixing and strong mixing very similar. When we have the probability of A of A intersected with B, we can look at it as, of course, the expectation of the indicator of A, indicator of B. But since A is measurable with respect to x minus, let's take everything until xt, is a loose notation. We could call this ft to be consistent with the notion of filtration we had before. So since the indicator function of A is measured with respect to ft, it goes out of the expectation. By the Markov property, this is the expected value of the indicator of B shifted by t at xt. So the only dependence we have between A and B is given through the last point xt. And this we can also bound uniformly because the distance between this and this sorry, let me, so the difference between this, it's uniform over the starting point. After some time, sorry, here's after some time s minus the expectation over mu of f. This decays exponentially. So in the end, we can replace this by the expectation mu of f, and here you have, sorry, of b, the probability of b, and here we have probability of a, and we are happy. So I didn't go into many details. This is an example that is more focused on whoever did Markov chains in the summers. But it's something that is easy to prove, that if a Markov chain of a finite state space is a periodic and irreducible, it mixes strongly. It actually mixes quantitatively in the following sense. If we define this quantity that defines strong mixing as alpha of s, then we can say that P mixes exponentially with respect to the shift if alpha of s smaller or equal than e to the minus cs for some c. So this is a quantitative bound on how well it mixes, that does hold true for the example one we gave. Okay, so I hope that you are kind of convinced when I draw the line like this, that we have IID here and mixing here. I hope you agree with me that mixing in its various forms is related to independence, because as we see in its own definition it has something close to independence here, but it's a weaker notion. And you have several forms of mixing, right? Strong mixing, quantitative mixings like this. And what I'm going to say now is that ergodicity is somewhere here. It's also some way to characterize probabilities on product spaces with respect to the shift, but it's a weaker notion because of the following result. So theorem, if we have a family a B infinite family that is stationary, or invariant, right? We define this meaning that if you apply to the shift, it's invariant with respect to the shift, and mixes, then it's ergodic. So here I'm using a different notation. I'm saying that the sequence is ergodic, meaning of course that the distribution that this sequence has on S to the Z is ergodic or mixing. So let's see how the proof goes. Here you see we are assuming some sort of independence and we're trying to extract the ergodicity. So let us denote by phi again the shift that goes from S to Z to itself. And we recall that the measure, the distribution of X, right, that we denote by P, is invariant with respect to the shift. So this is this stationarity. And since we are in a product space, we can approximate any event by a cylinder. So the sigma algebra defined on product space is the sigma algebra of cylinders using Theodori's theorem. So it means that for every event A, let's call it B actually. For every event B, we can find the event A that is measurable only with respect to X from minus K to K, and such that the probability of A approximates very well the probability of B. And this is what we are going to use as a notion of approximation. The probability of the symmetric difference is smaller than epsilon. So for every epsilon and every event, we can approximate this event by an event that's supported on finitely many projections. And this B here, we are going to take as a invariant event, because we're trying to show ergodicity, right? So we want to show that the probability of this event is 0, 1 for every invariant event. So take an invariant event, we can approximate it by something that only looks into finitely many coordinates. Okay, so in order to show that B has probability 0 or 1, which is our objective, right? We're going to show that the probability of B is equal to the probability of B squared. I mean, there's nothing here. I'm just saying that if an event, this probability is some number between 0 and 1. If it's the square of itself, then it's either 0 or 1. No other number can be in the interval 0, 1 can be the square of itself. So we are going to prove this using some sort of approximation. So instead of showing that it's exactly 0, we're going to show that it's very small. Okay, so first, when we're looking at the probability of B is an invariant event. So B is in fact equal to phi of B, which is actually again equal to phi 2 of B. Can iterate this as many times as we want. For every L, B is actually phi L of B. So this is part of being invariant. And here, that means we can write it as, of course, we can write the probability as this. There's no problem here. If this event is exactly this event, then we can write these probabilities to be the same. But even more than that, we can write this, right? I'm intersecting an event with itself. The invariance is not saying that the probability is the same. It's actually that the event is the same. So I can intersect it with itself and it doesn't change. But what's interesting now is that on one hand we have something that looks like probability of B. On the other hand, it looks like B appearing twice, right? So it's inspiration for getting this square here. So how do we actually get it? Let's go back to what we want to prove. The probability of B being close to the probability of B squared. Of course, the probability of B is already written here. We can replace it by B intersected with phi L of B. And here we have B squared. Okay, now what if we want to replace now B by this event A that approximates B very well? So there will be errors, right? Up to now we did equalities all the time, but now there will be some errors. As we replace B by something that is very close to B, we can actually replace, but we have to put, whenever we see B, we can replace it. Probability of A, squared. Here, these are the easiest replacements. If we do this, what's happening is we have to pay for the difference. We have to write the difference, like plus the difference between the things where we replaced A by B. And actually all of this, because of this probability of the symmetric difference being small, they're always multiplied by a number between 0 and 1. So all the time we're going to collect some epsilon here. Now, the only place that is a little bit hard to think is how to replace B by A here. Can we replace B by A inside the shift? Because B is invariant, but A is not invariant. Can we replace this by A here? Yes, we are not using that A is invariant. We are using that phi is invariant. So since the probability is stationary, it's invariant with respect to phi, but so you can replace B by A here and also pay one more cost epsilon here. So this is a calculation that you should break into several terms. Like you take the probability, you have terms like this, right? Probability of A intersected phi L of B minus, this is a parenthesis, minus probability of B phi L of B. And you're going to have to work with all these terms and show that all of them are smaller than epsilon. You have 4 terms of like this and you get a 4 epsilon. So I'm not going to do this, but it's a simple probability 1 calculation. But what's very interesting now is that B was an invariant event. So this equality was trivial. But this is far from trivial for A, because after we write this, we are not looking like something A intersected with A itself. Because after you shift, these become events that have very far away support. So A is supported somewhere between minus K and K. And this phi L of A is here, where L is this distance here. And we know that as L goes to infinity, this thing here converges to PA squared. So we know that this is smaller or equal than 5 epsilon for every L large enough. And actually the epsilon appeared here. We could prove this for every epsilon. So since this is true for every epsilon positive, we know that B is independent from itself. Or in other words, probability of B is equal to the probability of B squared, or the probability of B is between 0 and 1. So we have assumed that something is mixing, not even strongly mixing. And we use this to show that any invariant event is independent of itself by approximating it by some finite supported event and a copy of the shifted event, that's the same event. Again, we approximate it by another invariant event, and these are roughly independent. So we get that B is independent of itself. Since this holds for every invariant event B, we got that P is ergodic. So now we kind of have established that these various forms of mixing are all above the ergodicity in terms of how independent things are, so to say. And in the future class, we're going to prove a result for ergodicity, which we already know for independence. So another way to see these things is to think, okay, we know a lot, a big theory for sequence of IID random variables. Can we extend this theory to this line, to mixing or to ergodic results? So this is one way to see the theorems from ergodic theory, an extension of we already know for IID case in a more dependent scenario. Okay, so see you next class.